Hi, welcome to the lecture 9 of the DIC course where we are going to talk about sequential circuit design. Okay, and um, let's go over some of the fundamentals here. Memory elements, uh, memory memory elements. Um, or sequential elements, if you will, can be classified based on synchronization, um, and can be classified on the circuit type, or if you will, implementation. Okay. In terms of the synchronization, we have if we draw the clock level. Okay, so this is the clock signal. So this is the clock. In your textbook, they like to refer to it as phi. That's fine. It is a clock. Anyway, if your sequential element or memory element is level sensitive, and what we mean by level sensitive, it means that the sequential element, let's use a, has is open during clock high, open, or we sometimes use the word transparent. Okay, transparent when the clock is high, and closes when the clock is uh, or we sometimes we call it opaque, when the clock is low. Then we say that this element is level sensitive, and we refer to it as a latch. Okay. Meaning, what does it mean it's open? What it means, it's open that the clock, the output. So if we draw the latch here, we have typically a clock and an input, let's say D, and the output Q. Open means that the Q changes when D changes. That this is the meaning of a latch that is open. When the latch is closed, no matter what D changes, Q is not going to change because we stored the last value of a D. Okay. All right. So that's in terms of level sensitive. Then we have edge sensitive. Okay, edge sensitive, and it means that edge sensitive means that if I choose this color, that the sequential element is really sensitive only to the edge of the clock when the clock goes from low to high. Okay, in this case we call it pause edge, or it is triggered from when the clock goes from high to low. So this refer to it as flip-flop. Okay, and typically, okay, we draw it like so. We have a triangle here for the clock that indicates it's a flip-flop. We have a D here and a Q. So what do we mean is sensitive by the edge? It means that the Q value changes only at this edge if it is a pause edge. The Q changes with the value of D only at this time. Okay, so that's or if it is negative edge at this time. Most of the flip-flops are positive edge, meaning they change, the Q changes with the value of the D when the clock goes from low to high. That's a positive edge, and that's a negative edge. Most of the flip-flops are positive edge. Now, uh, typically you don't have a flip-flop which is a positive edge and negative edge. Typically it's either positive edge or negative edge, and most of them are positive edge, which means when they are triggered, uh, they are triggered when the clock goes from low to high. Another thing to indicate here is that if it is a negative edge, there is a bubble here at the end of this triangle. Okay, that indicates a negative edge. Okay, so this is the flip-flop. So the flip-flop is edge sensitive, and the latch is level sensitive. Okay, now in terms of implementation, the sequential element can be implemented as static implementation or dynamic implementation. So we have static circuit types and dynamic circuit types. Um, uh, 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 let me just say that from the we're going to get into the details of static, but typically static are more robust and larger. Dynamic circuit are smaller but sensitive to noise and leakage. Okay, so typically they are used for a very specific, very specialized purpose. From the above, from this discussion, we can really look at different flavors. If we draw some kind of, let's just use a different color here. So if we look at the classification, we looked at the classification of circuit based on their type and based on their the way we synchronize them. We say type is a static, could be static or dynamic, and synchronization can be latch or flip-flops. And now you can see, now we have four quadrants here, and we have four types of circuits that we'll discuss. We have static, latch, and static, flip-flop, and dynamic, latch, and dynamic, flip-flops. Okay, all right, so these are the four types that we're going to talk about in this lecture. Okay, based on we got these types based on the synchronization mechanism and the circuit implementation. Just one more note here, that in digital logic, we studied different type of flip-flops. We studied D flip-flop, T flip-flop, and JK flip-flop. Oops, sorry. We Okay, JK flip-flop. Okay, JK flip-flop. Now, um, for practical purposes, and because it's easy and because it's very well studied and implemented robustly, D flip-flop seems to be the most dominant of all the flip-flops. Quite frankly, in practice, nobody uses a T flip-flop, nobody uses JK flip-flop, probably very limited use. So we're going to limit our discussion to D flip-flop, and also as well D latch as well. You can take the same discussion to D latch. Nobody uses the other type of latches as well. So D flip-flop and D latch will be our main focus in terms of latches and flip-flops. Okay, so um, uh, the so basically here, you can see how we have classified these elements based on the synchronization and the circuit type, and we have got those four types of circuits that we'll discuss in this lecture. Okay, so let's move on now. Now, in terms of operation, in terms of sequential element operations, we're going to classify those into we're going to look at basic operations and um, um, enable operation using enable line, and set and reset operation using the set and reset lamps. So what are the basic operations? Let's take a look in here. What are the basic operation of a sequential element? The basic operation of any sequential element is two. This sequential element must be able to store data. Somehow we have to find a mechanism of storing data and access the sequential element. Okay, and in particular, write seems to be challenging, and you have to somehow to figure that figure the right operation. So when you create a sequential element somehow, and this is the sequential element, this is the D, this is the Q. Okay, somehow if you invent a new sequential or memory element, you have to tell me how I can store the data and how I can write a new data. These are a must-have operations. Okay, now in terms of the enable operation, sometimes we provide an enable pin. Okay, so here we have here we have, so I forgot to mention here, this is a clock here, and I'm assuming that I'm having a flip-flop. Notice this triangle here. This indicates it's a flip-flop. The absence of this triangle, it means what? A latch. Okay, so we will have to. So I'm gonna be consistent of my examples. Suppose I'm using flip-flops here. So is a clock. So if here is the D and here is the Q, and then I have this sometimes enable line, and the enable line is used for latches to put these latches into a sleep mode. Sleep mode. All right, when enable equals 0, meaning that the Q of the flip flop does not change with the D even when the clock is triggering, going to the rising edge or of this flip flop. So because the flip flop is in sleep mode, and typically this mode is used for low power low power modes. Okay, all right, and then we have the normal mode. Okay, it acts like as usual when enable equals 1. So this is another operation that we will discuss in this chapter or in this lecture, probably part 2. And then we have set and reset, and basically the set means that somehow you have to force Q to be 1, and reset somehow you have to force Q to be 0. And those type of operations are used when you initialize the system or the controller. Okay, so you force all the flip-flops to be zeros or ones. Okay, and we will look at two types of set and reset: synchronous set and reset, and asynchronous set and reset. Okay, so these are the type of operations: basic operations, enable operation, and set and reset. Okay, all right, so that's what we'll look at, and this and the, so I wanted to go through this introduction so that I prepped you of what is going to be discussed in terms of the terms and operation, the circuit types, so now you are aware with this intro of what we're gonna talk about in terms of these terminology that we'll use in this lecture. Okay, all right, now so let's start with the static delatch. Remember, we have 4 types. We said that we have static delatch, dynamic delatch, static flip-flop, dynamic flip-flop. We'll start with the static delatch. Okay, so let's see static delatch, how we implement it. Well, it's static delatch. People figure it out by try and error, by that if they have a chain of inverters, okay, and this chain is even number of inverters, then they create a loop where they can store data. Well, let's try that, for example. So for instance, let's say this point is 1, then this is a 0, and this is what? A 0. So this 0 is fed back again. So basically we are storing the data. Keep in mind that this is not the scenario if we have odd number of inverters. For instance, if we have, for example, this type of inverter. So let's see 3. Okay, let's see, we have a 3 here. Okay, so now if we have, say for example, a 0 here, then this becomes a 1. This is a 0. This becomes a 1. So we are forcing this to a 1, and this we're forcing this to a 0. We're forcing this to a 1. We're forcing this to a 0. So this becomes a 0, and this were. So now you can see what we created here. We didn't create a stable circuit. We have created an oscillator circuit. So this circuit is a stable circuit, and this circuit is an oscillator. Okay, now, so using the concept of a stable circuit, and by the way, this is stable circuit, it has an analogy in physical system. In physical system, if you look at for example, this type of physical experiment where you have, here we have a ball here, that right at that tip here, and we have here a slope, and we have here a slope. See, this ball can be pushed easy and settled here. Okay, and this ball can stay in this position. Let's say it's position A, this is position B, and this is position C. Position C is A stable, we call it, but it has a two stable situation where it's in A or B. So if I wanted to move it to B, I have to force it all the way up here, and then it will settle here. Okay, it will settle here and stay stable here. And similarly, this circuit here, it has, if I look at this voltage here, it has two stable voltage, a 0 or a 1. Now, if I want to change it from a 0 to 1, somehow I have to apply a force. I have to apply a force, and that force is typically the right operation. Okay, so let's say now, for this system to store and write, we will assume I would like to design a system where I have a D input. Okay, and this D input, somehow there is a switch here. Okay, and it goes to a feedback. Okay, and there is this feedback, somehow this feedback here. Also, somehow there is some kind of a switch here, and it goes up to here. Okay, and so this is a Q here. This is where I get my Q. Okay, and notice how many switches I am having. So I'm gonna indicate the switch by this something we can do on and off here, and there is a switch here that I can trigger this as an on and off. Okay, and we have the other switch here that closes and opens based on the operation. Okay, so we know that we need to do two operations, which is what? We need to do the store, and we need to do the write. Okay, okay. So based on this configuration, let's see how we can do a store, and let's see how we can do a write. Well, the store operation is very simple. What we have, this is my input. The first switch has to be opened. Okay, and then you have this feedback closed. The switch for the feedback is closed. Okay, and now you can see that the data circulates stable. Whatever we have stored, we stored. Now, suppose, for instance, so this is an inverter, back-to-back inverter, very stable configuration. This is for the store. Suppose I want to write the data. I want to change it. And in this case, what do? Here's the D input. The first switch now closes. And now, this is my inverter here. And the feedback has to be broken. So to break it, what do? I open the switch of the feedback. So now I open the switch, there is no feedback anymore, and then you can see the data. The data is going right inside this latch here. Okay, and so here's a Q, by the way, and this is here the Q. Okay, so now you can see that here we have the data circulates stable, whatever stored, and then here the data is being written to the latch. Okay, so now I provided the two operations. I provided the write and I provided the store. Okay, well, how about if I want to try to implement this circuit wise? Okay, all right. Well, so circuit wise, somehow we need to implement this. Where I can have the multiplexer in the rescue. How? Well, the multiplexer comes in and says, okay, I'm going to provide for you this switching mechanism where we either select the feedback or the new data. So this seems to be the point that I need to take care of here. So the multiplexer, here's the multiplexer. I either have the data or I either have the feedback. Okay. Based on some control signal, typically it's the clock. Okay. And here is you have Q, and here you have Q prime. Okay, so this is typically the configuration. So this is a 1 and this is a 0. Okay, all right, so let's see how we can implement this in CMOS. All right, let's see. Okay, so in the last discussion, what we said that we want to have we will implement the the static D latch using this multiplexer configuration where I have the D here, okay, and here is the clock, and here is my feedback back to back, okay, all right, and here is my Q. There are two ways to implement this. One way, obviously, okay, is to use multiplexer. Oh, we know the multiplexer can be implemented by transmission gates. Very easy. Transmission gates. Okay, so here is the transmission gate where I have one input, the D, and the other input is the feedback. This gate is in MOS, triggered by opened by clock. This gate is an in MOS, opened by clock prime. Okay, and uh, okay, that's fine. Okay, so and this one here is this is a PMOS, which is also triggered by clock, open by clock prime, and here is a PMOS which is open by clock, which is control. Sorry, I should say control by clock. Now the output of those. So this is the multiplexer so far. The output of this multiplexer goes to the first inverter, second inverter, and the second inverter gives the feedback. Okay, all right. So this is the feedback here. Okay, so when the clock equals 1, all right. So it means that the latch is open. Why? Okay, so let's see why. Because you will have this D goes in all the way, and I forgot to mention that here I have here I have this point Q and this point Q prime. Okay, all right. So now, so this is when the clock is open. So the when the clock is 1. Okay, so if I might use if I might use the eraser here a little bit, I want to indicate with the green, um, with the green here. So the green indicates when the clock equals 1, then the latch is open or transparent. How about if I use the brown color here, light brown, when the clock equals 0, so it is closed, which means I have the data comes in here, goes in here, comes in here. It is the latch is closed. So this is the open is for the right operation. And whoops, sorry. For the write operation, and the close is for the store operation. Okay. Okay. Now, in terms of drawing, sometimes people in your notes they draw it in this way, and I don't want you to be confused. See this here, this particular transmission gate here. They tend to push it in such a way that you think that what we draw is different, but they just rearranging things. So let me draw it the way they draw in the notes. The way they draw in the notes is the following. They draw this D. You have one transmission gate, and then you have an inverter, and then you have another inverter here. And notice the second transmission gate, they bring it right here, okay? And its output goes to this point, okay? And this is clock, this is clock bar, and this is here clock bar, and this is here clock, okay? This is D, this is Q, and this is Q prime. These are the same. These are the same. Okay. All what we did is we just rearranged this fella right here, the transmission gate. We just rearranged it. We brought it in a different way. Okay. All right. Okay. Now, so sometimes as well, what people use is that instead of sometimes the other note here that I have is sometimes, let's see if I open. We studied in tri-states that you can have this transmission gate and an inverter which feeds to it. Okay, it can be implemented using tri-state. So an equivalent to this design, it's not the same, but an equivalent in functionality is to use a tri-state. So here is a tri-state here. Okay, so this is let's say for example here this input here is A, and this is B. This is our clock. This is our clock prime. Okay, so here is your output B. Here is your input A, and here is your CLK prime, and here is your CLK. Okay, so these two are equivalent, okay, in terms of functionality, and therefore I can draw the latch in a different way. Okay, let's see how. So what I did last time, I said I can draw the latch as such: D latch, inverter, and then another inverter, and a latch here, I'm sorry, transmission gate, another transmission gate. Okay, so this transmission gate is activated by clock. This is a PMOS clock prime. This is an NMOS clock prime. This is a PMOS clock. Okay, and then we say this is my Q, and this is my Q prime. Okay, now I can redraw this latch using this tri-state, and I'm gonna use the symbol for this tri-state, which is this. Okay, okay, which is oops, sorry. So which is this. Okay, so we're gonna draw this like so. We're gonna say this is a D flip-flop. Okay, a D flip-flop, and uh, and goes to a transmission gate, and then you have an inverter. Okay, and watch, I'm gonna replace all of this with a tri-state. Okay, so this is a clock here. This is a clock prime. Okay, and this is my Q here, and this is my Q prime. Okay, now you can see these two are equivalent. Okay, this one uses transmission gate at this here, and this one uses a tri-state instead of transmission gate and inverter. Two equivalent latches. Okay, all right. At this point, we can go back to our lecture and our slides, and because what we will cover now, we're gonna go through the various types of implementations and see if I can. So we covered all of that. We covered all of that. We covered all of that, and we covered all the way up to here. Now we finished, or we touched upon the static latch. Let's talk about dynamic D-latch. Dynamic D-latch. And dynamic D-latch really is based on using a pass transistor. Here is your data, here is your output, and the output is saved on the diffusion capacitance of the pass transistor. Again, this is our clock. They like to use in your textbook phi as a clock. Now, somebody might say, well, wait a minute, is this enough? Well, this is an old latch. Nobody uses this latch anymore because of many problems. Let's see some. Well, let's talk about the good things about it. It's tiny, okay? It is low clock load. You can see one transistor using or needs a clock on its gate, which is an NMOS. But let's see the problems. The main problem, VT drop. What do you mean by VT drop? When we write a 1 here, it will not be VDD, right? It will be rather VDD minus VT. That's a major problem. You are impacting my noise margin here. Okay, what's the other problem? Leakage. So when the clock is 0 and this is supposed to be off, we know that there is a leakage current which can erroneously drain the VDD minus VT all the way up to 0 volt. So that's a major problem of this pass transistor. Okay, so two main problems. Now other problems: non-restoring. And non-restoring says basically that any noise here will be copied to the queue. Any noise on the D input will be copied, which is a bad thing. We would like to filter out the noise in our designs. Backdriving means that you can erroneously write the data from Q to D. So because we know that what we would like to do is that write from D to Q. But sometimes if you're not careful in your design, you can write data from Q to D, the opposite direction. That's another problem here. And this is because you're using just a pass transistor. And output noise sensitivity, the output is very sensitive to noise. And input diffusion, here, notice that the D is looking at an input diffusion. We don't like this input diffusion. First of all, the calculation, the capacitance is not trivial. Plus, sometimes you see the gate close, and sometimes you see it open. So we don't like typically this to be our interface in a latch. You don't like to be, this is your interface of a latch for the outside world. You don't like this diffusion, you don't like this other diffusion. And that's why people sometimes try to fix this by having inverters like so, where you isolate the input diffusion and the output diffusion from the outside world. Okay, but now this tiny advertisement pitch here is gone because they have to increase number of transistors. Okay, so to fix this droppage here, what people suggested says, okay, well, how about if we use, instead of pass transistor, we use a transmission gate. Okay, so we fix the VT problem because here now when we write a 1, we will write VDD instead of VDD minus VT. Okay, this is good, but we still have the major problem of leakage, because when phi equals 0, okay, and this is equals 1, and this device is supposed to be off, you will have a current leaking from here, from Q to D. And remember, we are storing this in a tiny capacitor, and this can easily be drained from VDD voltage to 0 volt. Okay, so this is another configuration of the dynamic latch using transmission gate. Notice the extra inverter here, okay? The extra inverter here at this position and at this position, okay? Okay, let's just double check. Okay, the recording is on. Sorry. Okay, so notice the extra inverter here or extra inverter here. And obviously, this inverter was added to solve the problem of having the output diffusion here. This diffusion facing the outside world. So we added another inverter. Issues? Well, yes, we isolated the outside world. Okay, but we added two transistors, and we have an inverted output here, inverted Q. Another thing here is that the input diffusion is still exposed. All right, so we can take the inverter then and put it in the to isolate the input diffusion, and now your output diffusion is exposed as well. Okay, so it's a matter of where you want to have the hit on the input diffusion or in the output diffusion. Okay, so every time you fix, you add extra devices. Still, the problem which persists: leakage not solved. Leakage not solved, and it is the main problem for dynamic latch and dynamic flip-flop, as we'll see later on. Okay, all right. Now, this configuration we looked at for the latch design. Okay, as we discussed in the whiteboard earlier. Okay, uh, this issue says back driving risk, which means if you have, for instance, a very large capacitance here, you could end up really writing the data from the Q to the D, and so you have to be But static means what? There is no leakage. That's the main advantage that you get from data is and this is robust latch. Okay, so with the exception of back drivability. Now you can start to fix it here and there by just saying, okay, let's protect the input, for instance. Okay, and we can go later on and say, let's protect the output here by so every time you add something, you're adding devices. So here you are protecting the input diffusion, so we added an inverter here. Here you're protecting this critical signal which stores the data, so we added an inverter, so to protect it from back drivability. Okay, so back driving. So now you have added more devices here to fix issues. But anyway, this type of latch very robust. Okay, extra few sizes here and there. The clock loading is high typically for static latch. This is well known. Okay, now people say, okay, we'll use this latch, and sometimes if you are sure about your input doesn't care so much about exposing this diffusion, we can eliminate that. But typically this is the standard D latch which is used in other designs. It is small relatively, not, not smaller than dynamic latches though. It is robust, and nowadays robust design wins all the time. Okay, with a large number of devices in our chips. So flip-flops, let me go back to my whiteboard here and do some discussion here because I want to show something about the flip-flop. So what we did so far, we discussed now the D latch, static, and dynamic. All right, so done with those. So let's take a look at the flip-flop. Okay, static and dynamic. Okay, so we're going to discuss those now. Okay, so in terms of um, the let's start with static flip-flop. Static flip-flop, let me draw the clock, and we said here's my clock. Here is my clock. So we have, okay, so the clock comes in low, stays here, goes high, stays here, goes low. And what we said is that for positive edge clock, this is the edge where we copy the what? The D data to the Q. Okay, so this is my for example, this is my flip-flop, this is my D, and this is my Q. All right. At this at this edge, I copy the D to the Q. That's why we say it's edge sensitive. Okay. So what happened? I end up using two latches. To design this, I need to use two latches. How are they? Okay, so these two latches, we'll call the first one as master latch, and the second one a slave latch. Okay, well, how are they organized when the clock is low and when the clock is high? Okay, so here is my master latch, and here is my slave latch. And when the clock is low, the master latch, what it does, it will write the data, meaning this feedback is open, okay, and we are writing D to the Q. Okay, so we call this, so this is open, we are not doing, so this is a write operation. The slave is doing a what? A store. The slave is doing a store at this point when the clock is 0. So the slave is doing this, so it's open and it's doing this kind of closed loop. Okay, okay. So when the clock is high, what happened is that we have the master. The master is in store, and the slave is in write. Okay, so basically the master has this configuration, and the slave has this configuration where the feedback is broken. So the combination, and watch here, the combination, when the master is a write and the slave is a write, watch, right, when these two guys are in write, because here the master is in write and the slave is in store. Okay, and here the master is in store and the slave is in write. Okay, operation, and all these are latches. We use these two latches to build what? To build the flip-flop, the D flip-flop. Okay, so the combination of whenever you do a master write followed by a slave write, watch, master write followed by a slave write, this is when you copy the D data at the input of the flop to the Q at the output of the flop, and this happens at this edge, the rise edge. Okay, all right, and to achieve this, what you will achieve it by activating this latch here by a clock bar, and this latch here by a clock. And that's why we say the way we build this, we draw it as two latches. Okay, there is this latch here activated by a clock, this latch activated by a clock bar, then the D input goes in here to the D input of this latch, and we call this QM, and then the Q goes to the D, and this is the Q of, this is the Q of the flip-flop, and that is now the boundary of my flip-flops. This is the boundary of my flip-flop. This is my flip-flop. It uses two latches, master latch and a slave latch. Okay, all right. So let's go back to our lecture now, and now with this illustration, and basically we are saying that. So this is basically what we talked about here in terms of the flip-flops, and we say that this is how this mechanism works. Okay, and to construct the circuit. Um, Okay, so let's keep going. And here's my circuit. So so you can see that here is the boundary of the first latch, and here is the boundary of the second latch. Okay, and you can see that a latch feeds over latch. This latch is activated. The first latch here is activated by clock, or it is open when clock equals 0, and this latch here The second latch is open when clock equals 1. So this is open when clock equals 0, and this is open when clock equals 1. The rest of the latch, by the way, is the same as we have discussed. Just notice here how these clocks, here it is clock prime, so that we open this when clock equals 0. Okay, and you can see that this is a clock prime here, and this is a clock here on the NMOS, and the PMOSs are the opposite. But for this latch here, it is open when the clock equals 1 and stores when the clock equals 0. Okay, this is because they have this opposite operation in terms of level of the clock. Okay, so this is our static latch. I'm sorry, this is our static flip-flop design. Two latches, one activated by clock prime and one activated by clock. Okay, sorry. Now, for dynamic flip-flop, it's the same. You can see that we sort of minimized this this flip-flop, okay, to two small latches here. So here is my first latch, which is the master, and the second latch, which is the slave. You can see that the master is activated or open at clock equals 0. He is using phi here, and the slave is open when the clock equals 1. Okay, and this is an extra inverter. Okay, so we're using similar organization to this one. Now you can see we are adding some extra, so you can see the parallelism here between dynamic and flip-flop in terms of we need to have a master latch and slave latch. The static flip-flop here, he's adding extra inverters on the input to alleviate the load on the input diffusion here, and he's adding extra inverter to the queue to alleviate the load on the internal node of the flip-flop. Okay, so these are for robustness added, as well as he adds here an extra inverter in the dynamic latch to alleviate here the load on this diffusion node here. Okay, so again for extra robustness of the flip-flop, both for the static and dynamic. Okay, I think this is what I will stop here for this part, and we'll discuss the rest of the lecture in the second part, and thank you for listening.